Okay, so let's start today's seminar. Um, so I was told that this seminar is going to be the most interesting one because it's going to talk about the AGM Bound. Okay, we've come a long way. All right, if you think about it, we started with cyclic queries. Okay, and um, and then starting from the previous seminar, uh, we we um, marched into the territory of cyclic joints. Okay. Um, so one difference between a cyclic joints and cyclic joints is that for a cyclic joints, as you can see, we're able to process them very, very well. Okay, basically in an output sensitive manner, right? So you can do in plus out if you still remember, right? So in stands for the input size of a joint, and out stands for the output size of a joint. Okay. So I can tell you such a complexity is unlikely to be possible for cyclic joints. Okay, unlikely. Okay, in plus L. And currently, the state of the art for cyclic joints, at least one uh, way to interpret the state of the art is to achieve this so-called worst case optimality. Okay, worst case optimality. Um, so this is how today's seminar um, gets connected to the previous seminar. Okay, so in the previous seminar we talked about subgraph enumeration, which is, I would say, an interesting special case of joints in general. Okay, so one very important message from the previous seminar is that if you want to deal with a problem like subgraph enumeration, and you want to claim optimality, okay, so you want to follow some sort of principle to study this problem with, let's say, very attractive worst case guarantees, and what would be uh, the intended approach. Okay, so that was the main purpose of discussing, subgraph enumeration, right? So we saw that basically the idea is to first set a very good target, and then you try to prove that you are able to meet that target with an algorithm. Okay, so this is again the approach that we will take today, and as I said, this is one way to interpret the state of the art. Okay, not the only way. Um, in fact, for cyclic joints, people have also made some progress in terms of output sensitive algorithms, but this is not our topic today. Okay, so actually that topic is much deeper. We'll have to go into some modular width and also panda algorithm, et cetera, et cetera. But today we'll talk about worst case optimality. Okay. So before I start, let's quickly review some concepts. Okay. So first of all, tuple. All right, tuple. A tuple is defined as a function from um, from a set of attributes. Okay, so here this X here represents a set of attributes. Okay, and this n represents the set of integers. Okay, so once again, a tuple is defined as a function. Okay, so you can see that we always have a set of attributes in mind whenever we talk about a tuple. Okay, so this X here, I'm not going to formalize it further, but you can think about every attribute as just some element from some set. Okay, it doesn't really matter. Okay, so I'm going to use English letters to represent attributes um, in my presentation today. Okay, good. So that is the definition of a tuple. And another very important definition is this relation. I told you that every tuple is defined over a set of attributes, right? So what is a relation? A relation is nothing but a set of tuples defined over the same set of attributes. Okay, so whenever I say R, so once again, I said R is a set of tuples defined over an identical set of attributes. You see what I'm saying? Okay, and every tuple is a function, right? So essentially, this relation contains a lot of functions. Okay, so so when I say the schema of a relation, I refer to the set of attributes over which its tuples are defined. Okay, um, so everything so far should be rigorous. There should be no ambiguity. Okay. So for instance, if I say, okay, let's consider a relation with schema AB, okay, and then you should imagine a few things. First, A and B, they are attributes in the schema of the relation, right? So if I say schema parenthesis R, and this is just a set, and this set contains A and B, okay? And furthermore, you should imagine that inside this relation, you are looking at a lot of tuples, okay? And every tuple is a function. So for example, if I can, so I can say A1, P1. So, that's basically, those are basically the function values. Okay. But that's just one tuple, and you can have as many as you want. Okay. All right, cool. So that is the definition of a relation. And now let's talk about the definition of a join. Okay. So a join today, we can adopt a relatively simple definition compared to what you normally see in a database theory textbook. Okay, so we will define the join as simply a set of relations. Okay, so once again, so far all the definitions should be mathematically sound, and there should be no ambiguity. Okay, all right. So any questions so far? No, okay. So let's look at an example that will allow you to draw connections to subgraph enumeration that we talked about last time. Say here I have three relations, AB and AC, and also BC. Okay, so I'm going to refer to the first relation as RAB, and this subscript AB reminds you of its schema, right? And then our AC and then our BC. Okay, I have three relations here. Okay, um, so now we have to define its result, right? The result. So the result, which I denote as John Q. Okay, so this is a relation itself. This is a relation. All right. So every time I talk about a relation, you should ask me, okay, what is the schema of the relation, right? Otherwise, some definitions are missing, right? So this relation for John in my running example is a relation. The output of this John in my running example is a relation with attributes A, B, C. Okay, so in general, it includes all the attributes in the relations in the join. Okay, good. Now this relation consists of all the tuples. This U. Okay. By the way, let me define this schema of the relation as schema Q. Right. So this is once again, as I said, the union of the all the attributes appearing in the participating relations, right? So this you can formally define it as follows. You look at every relation in the join. Now you see this R in Q is rigorous. Is rigorous, right? Because a join has been defined as a set of relations. So you look at the union of the schemas. Okay, so this is the schema of the output relation of the join. And now I give you the content of the join result. Okay, so we look at this um, definition. So here, conceptual, right? You can try to find all kinds of tuples that are defined over the schema. So for example, ABC, right? So so far, you can find so you can look at any tuple that you can place into ABC. Of course, not every such tuple gets to appear in the joint result, right? So that's why you have a condition, and the condition says, for every relation in the joint. Okay, so if you look at this is schema R, right? So this is schema R. Sorry, just let me. Okay, so for every relation inside the joint, the following we have to hold. You take a relation and you look at the projection of U. This block parenthesis, the square parenthesis, square brackets represent the projection of the tuple. I defined all these things before. Today I'm not going to redefine them, but we'll see this with this. I'll illustrate this with this running example if this is not completely clear to you. But to complete the definition of the joint, this is the definition. Okay, so essentially it says, well, you're welcome to try any tuple conforming to the schema. So for example, you try 1, 2, 3, right? However, not every such tuple gets to satisfy the condition that I have here. And therefore, not every tuple that you can fit the schema gets to appear in the joint result. You see what I'm saying? So in order for this tuple 1, 2, 3 to appear in the joint result, you need to satisfy 3 conditions. All right. So basically, there are 3 projection checks. Okay. The first projection check says, okay, I look at this AB. That's the first participating relation. I look at the projection of this tuple over AB, right? And then you get a tuple with 2 attributes, right? 1 and 2, correct? Okay. And then you ask the question, does this 1, 2 appear in RAB, right? So this is the first check. You see what I'm saying? And for this tuple to appear in the joint result, it will have to survive 3 checks. Okay, you have to. So in my running example here, you need this 1, 2 to appear in RAB. You need this 1, 3 to appear in RAC, and finally, you also need BC to appear in RBC. Okay, is that all right? Okay. Now, if you think about it, this will make it rigorous, and this is consistent with the natural joint definition you should have learned in your database training. Right. Okay. Cool. So this is the joint result. Good. So the joint computation problem is to compute this joint result. Okay, when you have a set of relations, any set of relations defines a joint like this. Okay, so the purpose is to compute the joint. All right, and we want to have an algorithm that we can claim worst case optimal. All right, so that is the business today. Very nice. Okay, so currently we are. By the way, just one more remark. Today I will assume this is so-called data complexity. Okay, data complexity. So basically, this says the number of attributes that you can have, the total number of attributes you can have. In this case, ABC. Okay, but in general, this means the total number of attributes you can have is bounded by a constant. Okay, why? Well, you have to go back several seminars. In the beginning, I proved that the joint problem is unlikely to allow a polynomial time algorithm. Why? Because even detecting whether the joint results empty, if you do not impose such a data complexity, constant schema, constant number of attribute assumption, in general, right, the problem of detecting whether the joint results empty is NP hard, right? So I prove a reduction from 3 set, right? Okay, so in practice, of course, this assumption is much less controversial, right? But in practice, you do have a limited number of attributes, especially compared to how many tuples you have, right? Okay. So now we are at a juncture that requires our thinking. Okay, so this is basically a familiar moment for us because we encountered this moment last week, right? When I talked about subgraph enumeration, I said, okay, at this point, how would you proceed? if you want to tackle this problem, is what I'm saying. But ideally, I would like to have something like what Yanakaki's algorithm is able to give me, something like in plus out. That would be perfect. Okay, that would be perfect. Okay. Well, I can tell you today, computer science is very skeptical about the existence of such an algorithm. Okay, so to cut a very long story short, the state of the art is basically telling you, people can do this so-called in. They cannot do in plus out, but they can do in to the power of some so-called some modular width. But for you, it's just some constant that is probably greater than one. Okay, and that constant depends on the given join. Okay, and there is some evidence showing that this is very likely to be optimal. Okay, and therefore, if you want to do in plus, if you want to do output sensitive, and then you will aim at something like what I said, right? So this maybe something like in to the power of something plus out, right? So that's one way to approach the problem. Okay, that's one way. Another way to approach the problem, which is easier, is to try to find worst case optimal algorithms. Okay, now if today this is the direction we will go down. Okay, and then in order to make the direction work, we have to answer two questions. The first question is, what time complexity should be regarded as being worst case optimal, right? And the second is, okay, how do you achieve that time complexity? If you think about logic, right? So this is how we should go, right? Good. We answered the question for subgraph enumeration last week. We talked about this fractional edge cover number. All right, you're not going to see fractional edge cover number today. Okay, and also the processing algorithm will look drastically different from what I gave you last time. Okay, this is not surprising. Why? Because subgraph enumeration can be reformulated as a join problem. Okay, so this is not something I will go into details about which I'll go into details today, but this will be something very good for your thinking. Okay, so in general, I give you, for example, triangle listing problem, right? How are you going to convert it into a join problem, right? And the hint is that you want to create three relations. Okay, intuitively, in a triangle, there are three edges. Okay, so you want to create three relations. And then you want to argue that if you can solve the join on those three relations, and then basically you solve the triangle listing problem. And furthermore, you have to prove that you have very little overhead. You see what I'm saying? Because the total amount of time, I mean, no matter what you do, pre-processing, post-processing, all this time will be counted as the time of solving triangle listing. Okay, you have to prove that even the overhead is bounded by if you still remember the time of solving triangle listing, right? So n to the power 1.5. Okay, so you have to prove everything's doable in n to the power 1.5. Okay. So today we tackle a more general problem. Okay, so this join. All right, so in general, it doesn't have to be defined over relations with just two attributes. Okay, those are binary relations. All right, so in my running example, all the relations are binary, but in general, they don't have to be. Okay, so it can be ABC, you can join ABC with BCD, etc., right? So if you think about it, the problem feels hard, right? Feels hard because now I'm not saying, for one join, find me an algorithm. I'm saying you want to find me a blanket algorithm that works for all join. You see what I'm saying? Okay, good. All right, so two questions. The first question is, what should be the target time complexity? This is the first question I'm getting at today. Okay, and then the second question is how to design an algorithm meeting this time complexity. Okay. All right, so speaking about this target complexity, so once again, the methodology, same as before, right? Same as subgraph enumeration. The right question to ask here is, what will be the largest number of tuples in the join result? Okay, and this number serves as a way to measure the target time complexity because, obviously, you have to spend constant time, to even just outputting a tuple, correct? Okay. All right, so this is where the AGM bound comes in. Okay, so AGM bound tells you precisely, asymptotically, okay, asymptotically the number of joint tuples, of joint result tuples. Okay, so I'm going to define this AGM bound. Okay, here. Well, with the experience from subgraph enumeration, it should be a lot easier for you to grasp this AGM bound here. Um, in general, let's define the schema graph as follows. Okay, schema graph. Okay. Uh, if you give me a joint Q, now remember, right? So this Q is defined as a set of relations. Okay. I have already defined this schema Q. Once again, that is the union of the schemas of all the participating relations. Basically, it's a set of all the attributes, right? So the schema Q is simply defined as the um, set of vertices in this graph that I'm defining. Okay, so this is the definition of V. But I still have to give you the definition of yi, okay? There's a big yi here. Now, something very important is that this schema graph, this G, right, schema graph of Q. So this schema graph is not an ordinary graph. This is a hypergraph, okay, hypergraph, which basically says that each edge of the graph doesn't have to be binary, okay? It can contain any number of vertices, okay, including one, okay? So here, this yi is formally defined as follows. So you look at every relation in the joint, all right? And as I said, this relation has a schema, okay? The number of the set of attributes in the relation, right? And if you think about it, right? So this schema R, by definition, is a subset of this V, right? And that represents a hyperedge. Okay, that represents a hyperedge. And therefore, if you look at my running example, you will see, that's just triangle listing. Why? Because if you think about the schema graph, essentially it says the following, 3 vertices, right? And this is an edge. This is the edge defined by the relation RAB, right? And similarly, you can generate the other 2 edges, right? So this is the schema graph. However, it doesn't have to be binary, right? So let's say, just a very simple example, let's say ABC, BCD, and BDE. Okay, let's say ABC, BCD, and ABD. Okay, all right. So in this case, if I say what is the schema graph, well, it's more complicated, even if you want to draw it. All right, so this is these are the vertices. Now ABC, if you want to draw such a graph, this is how I would draw it. Okay, so this is a hypergraph. And for BCD, it will be something like this. ABD will be some ABD. Let's do it in another color. ABD. Okay. All right. So that's the schema graph of this joint. Okay, good. Very nice. And now, now that we already have this schema graph, we can define what it means by this fractional edge cover. This is pretty much the same as last time, except that here we extend the definition to arbitrary hypergraphs. Right? So in general, you want to have a vector. So I talk about vector here. So this W is over the space of E. Okay. Well, in case you are not familiar with the jargon, we're talking about vectors, right? Whenever I talk about a space, essentially I'm talking about dimensions. You see what I'm saying? For example, the X, Y, Z space. All right. So this is something you are familiar with. However, here it's more abstract, right? So I have this set E defined, right? Once again, this E is a set of hyperedges, right? So you consider every hyperedge as a dimension, all right? Just a name. You see what I'm saying? For example, here I would say dimension ABC, dimension BCD, etc., correct? So when I say this W is a vector over that space, essentially I'm saying, this is just a 3-dimensional vector, okay? Rather than calling it X dimension, I call it ABC. You see what I'm saying? So that's the meaning of saying that W is a vector over E. You see what I'm saying? Okay, good. And then for every E, for every small E, which is a hyperedge, right? And also a dimension of the space, right? Okay, that should be clear, right? So for every small e of this space, right? You have a component, right? WE, right? Component, right? So basically coordinate, right? Except that this is a fancier name used in vector analysis, right? So when I say a component, essentially I'm saying, okay, just look at the dimension, the corresponding dimension, and what's the value of this dimension in that vector. Okay, good. So you give me this W, and you can think about it as saying that uh, you would like to take this edge by the portion, by a fraction indicated by this component. You see what I'm saying? I don't know if you watched the video last week, because I talked about edge cover. All right. So in general, edge cover says you want to grab edges. Edge cover, right? You want to grab edges to cover vertices, right? So this is the opposite of vertex cover. All right. So very confusing names. The vertex cover says you want to grab vertices, but then the purpose is to cover edges, right? So here, edge cover, right? So you want to grab edges, and you want to cover vertices, right? But normally when we say we grab an edge, it's like a binary thing, right? You either take it or you leave it. You see what I'm saying? So think about weight, right? So it's either 0 or 1, right? But we're talking about fractional edge cover here. See what I'm saying? So it doesn't really have to be 0 or 1. You can say, okay, let's say 0.8. That would sound weird if this is the first time you get in touch with it, right? That would sound weird, but mathematically, it doesn't have to be weird, right? So essentially saying, you can imagine that, I take this edge, however, it's like 80% of it, okay? So that's why fractional edge cover is what I'm saying, all right? Now, but it still has to be an edge cover. You see what I'm saying? Edge cover. So in other words, every vertex will still need to be covered, right? So in a traditional 0, 1 edge cover, basically it says every vertex will have to appear in at least one edge of your choice, right? So now here we're talking about fractional edge cover. And then essentially we're saying for every vertex, let's say V, okay, inside this schema graph, the following will have to be true, right? So you look at all the edges that you have chosen. You see what I'm saying? I look at all those edges covering this V that you have chosen, right? And now remember, every edge has been given a weight, right? So it represents how much of it you want, right? And then the total weight of all these edges will have to add up to be at least 1, right? So this is going to make it consistent with the traditional edge cover concept, right? Formally speaking, this is saying, if you look at all the edges, such that this V, small v, is inside that edge, right? And the weight of this edge will have to be, sorry, the weight of the total weight of all such edges will have to be at least 1. Okay. If so, and then this vector W is said to be a fractional edge cover of this hypergraph, right? So this is basically the same as before, an extension of what we saw last time. So far, so good? Yeah, good. Very nice. Now, next, I'm going to define the so-called AGM value, not AGM bound yet, okay? AGM value, right? So every W gives you an AGM value, okay? Now, what is this AGM value? Look, when you give me a W, a fractional edge cover, right? I have every right to say, okay, now for every relation, you have something for me. Does this make sense to you? Okay, can you react to this quickly? All right, you give me a W, right? And then I say, okay, I look at every relation, R, you have something for me. You understand what I'm saying? What do you have for me in this vector? Well, you see, for every relation, you have a schema, this small e representing the schema of the relation. You see what I'm saying? All right. And then what is the thing you have for me? This WE. You see what I'm saying? Okay. So for every relation, you have something for me. So that's what I take. All right. Actually, I will put that in the power, okay, in the following expression. Okay. So I take that relation, I look at its size. By the way, this R subscript E, right? You say RAB, RBC, right? So that's the meaning, right? So the relation corresponding to the hyperedge E. Okay, so this is the size of the relation. By the way, the relations, the input relations do not need to have the same size, right? So this is one major difference from subgraph enumeration. You see what I'm saying? So I take the relation size, and then I take the thing that you have for me, which is the component of your vector, right? Fractional edge cover, right? So basically the weight on that edge, right? And then I raise it. I raise the cardinality to the power. Okay, all right. And then I multiply everything, multiply all the terms. See what I'm saying? Okay. So this is the AGM value that comes with the W fractional edge cover vector here. So far so good. Okay. No AGM bound yet. Okay. AGM value. So far so good. Okay. Good. Well, there is one important theorem. Okay, so this is theorem 1 in my lecture notes. Okay, so the important theorem says that okay, theorem 1. All right. So if you look at the size of the joint result, still remember this notation, right? Q, that's a joint, and joint Q, that's a relation. All right. So this is the output relation of the joint. Right? So a relation is nothing but a set, right? So that's why the pair of vertical bars make sense, right? Okay, so this is the output size, correct? Okay, this is bounded by the AGM value. I'll just write it in words. Okay, the AGM value of any fractional edge cover vector, any fractional edge cover of the schema graph W. All right. Again, I'm not talking about AGM bound. Okay, this is just a theorem. All right. So the what is non-trivial about the theorem? It says this holds true not only for some fractional edge covers, it actually holds for all of them. Okay. So this is a powerful theorem. And now we define the AGM bound. Okay, so once you see something like this, what's your immediate reaction? You say, okay, great. Okay, so we want to minimize the right-hand side, right? Because since any AGM value, any fractional edge cover is going to give me an AGM value that serves as an upper bound of the joint, right? So very naturally, I want the best one. You see what I mean? Here, the lower, the better, right? So I want the fractional edge cover, W star, whose AGM value is the lowest among all the AGM values. Okay, and that minimizes the right-hand side, right? So that's basically the best you can do according to the theorem, and that is our AGM bound. Do you see what I'm saying? Okay, so this is how the AGM bound is defined, right? So if you still remember what we talked about last time about subgraph enumeration, we were able to simplify the definition here because we had a very important property that all the input relations have the same size. Okay, so and then you can simplify everything, and that's how we came up with this fractional edge cover number, which you won't see today. Just a very quick remark. If you look at the definition more closely, you will realize that this is in order to find this W star. By the way, this is still something that you have to do in practice, right? If you want to derive this AGM bound, you have to find the optimal W star whose AGM value is the lowest, correct? Okay, but how do you achieve that purpose? Is what I'm saying. Okay, so you would say, okay, look at this product. Okay, so you want to minimize this product, right? But if you don't do it in the right way, this could be quite complicated, right? So so this is the remark. The remark says, you can actually convert this into a linear programming problem. You see that? Okay, because you can take the log of this, right? Take the log of this, and then this WE appears before the log, and then this log RE essentially becomes a coefficient. So every WE serves as a variable in this linear programming instance. and then you look at the constraints that it has to satisfy. Basically, um, uh, you know, these are the inequalities in the linear programming instance. Good. All right, so this is theorem number one. Okay, we'll give a proof of this theorem next week. Okay, next week. Now, if this is the only theorem you have, you should not be satisfied. You see what I'm saying? Because this does not really give us what we set off to seek in the beginning. Look at the first direction here, right? Target complexity. All right. So this theorem has not really answered that question. Okay. One thing that we still want is the tightness. You see what I'm saying? Is the tightness. All right. So this basically says the right-hand side is the best I can do according to the theorem. However, it does not really eliminate the possibility that even the best you can have is still too loose. Right? Okay. So there's another theorem which is about the tightness of this bound. Okay, it turns out that this bound is tight. However, we have to interpret this tightness in a very careful manner. All right, now this is once again related to subgraph enumeration. If you think about what I talked about last time, right? In subgraph enumeration, for example, think about triangle listing, right? What did I say to justify a bound like m to the power 1.5? Did I say, for every input graph, the number of triangles will have to be at least m to the power 1.5. That's clearly untrue. You see what I'm saying? Because you can give me a cyclic graph, and then there are no triangles at all, right? So how would you interpret this worst case complexity? So this is something very important. So what I said was that for every parameter m that you have in mind, every one of them, you see what I'm saying? For every parameter m, right, defines a set of graphs. You see what I'm saying? So basically, you look at all the graphs with m edges. All right, so that's a class of graphs, right? So what I'm saying is, for every m, there exists at least one graph with m edges, and this graph has at least m to the power 1.5 triangles up to a certain constant. You see what I'm saying? So this is how we interpret this worst case complexity. All right. Why does it make sense? It makes sense because if you indeed have a subgraph listing algorithm, this algorithm is supposed to work on all the graphs. You see what I'm saying? And if m is the only parameter you want to use to measure the efficiency of an algorithm, and then what I just said makes sense. Okay, and then I can be in your adversary. I can look for a graph, satisfying this parameter m, but it tries to kill you as much as possible. Same thing, same principle should be applied here. Okay, so this is why it's very important to look at the so-called cardinality vectors. Okay, cardinality vectors, right? So let's say this is CAR, cardinality vectors. Now this cardinality vector is defined over the same space as the W, as W. Okay, so this is a cardinality vector defined over the set of hyperedges, right? Or in English, essentially it says that you look at the joint schema. Okay, you look at the joint schema. So for example, ABC, BCD, ABD. All right, so look at the joint schemas. But in addition to that, you also have to give me three more values, three more cardinality values. Okay, cardinality for ABC, cardinality for BCD and ABD. You see what I'm saying? All right, good. And that's CAR. You see what I'm saying? So in general, if you have a joint problem, right? So you look at the schema, right? And then you say, all right, I give you an arbitrary cardinality vector over the joint schema. Okay, so basically you say, okay, on this relation, I constrain how many tuples it can have. Okay, at least so many tuples, at most so many tuples, right? Good. So every cardinality vector, right, this is CAR, defines a class of joint inputs. Okay, I hope you can understand it. You see what I'm saying? All right, so basically the same idea as what I said, the class of graphs subject to the size m, right? Good. Now, The promise is that for every cardinality vector that you can come up with, every one of them, okay? By the way, as you can see, once you have defined the cardinality vector, right? Once this thing is defined, the AGM value is defined. You see what I mean? And therefore, the AGM bound is defined. Just a very quick test. What is an AGM bound again? This is the AGM value of the best cover, right? So W star. But W star depends on only the cardinality vector. You see what I'm saying? All right. So the promise here is that for every cardinality vector, you can always find one John conforming to the cardinality vector. And the John output is at least the right-hand side. Okay. Actually not the right-hand side here. I mean the AGM bound that you can derive, this W star, okay, up to just a constant factor. That's what I'm saying. Okay, good. So proofs of these two theorems are not trivial. I won't have time today. So the proof of theorem one will be given in the next seminar, and the proof of theorem two will be given in the last seminar. Okay. So today we will proceed to talk about the second direction, not the second direction, to address the second question, right? So you see, we've already done the first question, target complexity, right? So now you have the target complexity. So the next question says, okay, what would be an algorithm? Okay, algorithm meeting the target time complexity. Okay. So you already know there is an AGM bound for the join. Okay, so let's just denote that as AGM. All right, so this is no longer AGM value. This is really the AGM bound. All right, and you can define the AGM bound based on the cardinalities of the relations. Okay, so far so good, right? Good. So now the question becomes, how would you be able to find an algorithm whose running time is bounded by this AGM? Okay. So I can tell you in database theory, people don't really care about polylog factors. Okay, so they call AGM, I mean, any algorithm whose running time is AGM times polylog of the input size as worst case optimal, right? So this is quite standard. Well, here, obviously there's some sloppiness, right? Because in theory you can still try very hard to minimize the power on the polylog, right? So that would make sense, especially from a practical point of view, right? I can also tell you under certain assumptions, it is possible to have an algorithm whose running time is strictly AGM, right? Under some assumptions. But then the algorithm will become quite complicated. And in my opinion, it's not very suitable for a seminar like this. Okay, it's in my PhD course, that was a 3-hour lecture. Okay, so I'm not going to do that today, obviously. All right. However, the interesting thing is if you don't mind a polylog, actually just I think a single log, and then there exists a very simple algorithm. Actually, there exist many algorithms that are much simpler than the this AGM time algorithm. Okay, and I would say one of them, this is something I'm going to talk about today, and one of them actually reviews a very nice very nice property of the mathematical structure behind the John problem. Okay, so this is the so-called split theorem. Okay, so once you understand the split theorem, you will be able to do a lot of things with it. Okay, including designing an algorithm to solve this problem in a worst case optimal manner. By the way, that means AGM times some polylog, right? Actually, this is something even more important. Once you know the algorithm, once you know the split theorem, immediately you can get a sampling algorithm. Okay, so still remember the sampling problem. Still remember the sampling problem? I defined it several weeks ago. So the problem is you want to pre-process the join, okay, linear time, okay, up to some polylog, okay, n log n, let's say. And then I want you to, without computing the join, right? I want you to give me a tuple drawn uniformly at random from the join result, right? So challenge is you don't want to compute the join because computing the join would result in AGM time, right? Which is big. You don't want to do that, but still you want to pretend as if you had done that. Okay. Whenever I say I want a uniform sample, you will say, here it is. but the time that you actually spend is AGM divided by out. Okay. Out, by the way, is the output size. Okay. As you can see, if out is just one, you don't really gain anything from AGM. You don't gain anything compared to spending AGM time, right? This is actually something open in computer science today, right? Are you able to detect emptiness? Basically, if you can find me a sample that indicates that the result is non-empty, right? If you cannot give me any sample, and then basically you're declaring that the result is empty, I can tell you for arbitrary joins, right? If you want to detect emptiness, currently still the fastest algorithm that works, blanket algorithm I'm talking about, right? The blanket algorithm that works for all the possible joins still requires AGM time. Okay, so that's why you should not be too disappointed at seeing, a time bound like AGM divided by L, right? Because here basically says if L is large, and then you start to gain significantly compared to the computing the entire join. See what I'm saying, all right? So of course, if L is AGM, then you're the happiest, right? So because you will be able to get a sample time just constant time, right? Okay, good. Just for the record, right? So if you talk about so-called combinatorial algorithms, which do not use matrix multiplication, right? There is some evidence indicating that AGM divided by L is pretty much the best you can do. Okay. All right. So next, I'm going to talk about this so-called split theorem. Okay, the split theorem it by itself has nothing to do with any algorithms. All right. So this is really just a theorem on the mathematical structure of the problem. Okay, but that's how computer science people, or in general, math, right? That's how people gain deeper and deeper understanding about each problem. Is what I'm saying. So every time we see something, we find something useful at the structure level. And then maybe we'll be able to utilize this property to design algorithms, right? However, the value of this theorem, I would have to say, is more than just allowing to design an algorithm. Okay, good. So in order to introduce the split theorem, I'm going to use my running example again. So this is an example that you are very familiar with, right? RAB, RAC, and RBC. Okay, good. So as I said, right, if you want to look at the joint result, you should be looking at a relation with three attributes, A, B, C, okay? And I also said that every tuple value is an integer. Do you remember I said that, right? Because, basically it doesn't really matter, right? As long as the value is in some domain that is countable, and then you can always map it into the set of integers, right? Okay. Now, why is that important here? This is important here because I want you to think about the output domain as a space, a three-dimensional space. Okay, you see what I'm saying? A three-dimensional space. Now, this is something important because once you get into the three-dimensional space, right? So let's say N3, right? So N3, and then immediately you put yourself in the the um, the realm of geometry. You see what I'm saying? Okay, and this is promising because we are very familiar with geometry, right? Geometry has been studied many for a very long time, right, by many people, and therefore, if we start to relate the problem to something, to a field about which we know quite well, and then this is promising, right? So this is in general very true for research, right? And indeed, as you will see, the split theorem benefits from geometry. Okay, both in terms of the analytical proof and also in terms of concept. Okay, so from now on, I would say, okay, now look at the space, right? So this n to the power of 3, okay, and then we will look at every point in the space. If you look at a point, right, small a, small b, small c, right? So that is just a three-dimensional point, right? And then you can view the joint result from the perspective of three-dimensional points. You see what I'm saying? Now you can imagine, you have all the possible three-dimensional points. You can grab one and then test whether this is a point corresponding to some tuple in the join result. I already I already told you how to test the membership, correct? Right? So you all you have to do is to do projections, right? But doing the projection is easy, right? It's constant time doable, right? So I ask you, oh, small a, small b, does that tuple exist in RAB? What would you do? You would say, okay, I'm going to create a hash structure or binary search tree because we don't really care about polylog factors, correct? Okay, so that's something very easy to do, right? Good. So that's another way to look at the join result. So now you can already imagine, I have all those potential point result points in the three-dimensional space, right? So now the goal is to find them. You see what I'm saying? Okay, so every one of them gives you a label 0 or 1. Now you simply want to find all those points carrying the label of 1, right? So it's almost like a machine learning classification problem now. Right? Okay, pretty nice. So this n to the power of 3, this data space is infinite. Okay, and we don't want infinity here because that's too intimidating, right? Too scary, all right? So we want to confine the space into something finite, right? And fortunately, this is fairly easy, right? So I have every right to say, well, let's just look at this space instead. Okay, by the way, this in is the total number of values in the join, or the total number of tuples, because they differ. Let's say the total number of values in the join, all right? So this is the input size, basically, okay? So I would say, you know what, from now on, let's restrict our attention to this in to the power of 3, okay? Rather than the whole integer domain, you see what I'm saying? Does that make sense to you? Okay, does that make sense to you? It makes sense because you can do mapping. You see what I'm saying? So for example, you can sort all the possible values in the relation, right? And then you can rename them, right? So in terms of ranks, right? So the smallest value gets to be called 1. Okay, the second gets to be called 2, etc., etc., right? So essentially, you don't really have to look at an arbitrary three-dimensional space, and suffices to consider the problem here. You see what I'm saying? Good, very nice. So now basically the problem becomes I have this space and I have potentially n to the power of 3 points, right? So for every point you can test membership in constant time, or I don't care about polylog, all right? So I'm gonna say constant time, interpret it as polylog, okay? So how would you be able to compute the join fast, right? So this is the problem we're looking at, right? So immediately n to the power of 3, that would be a trivial bound. You see what I'm saying? Okay. Now let's look at a box. All right, so let's think about a box. This is a box. Now, mathematically, what is a box? This is essentially an axis parallel rectangle. Axis parallel rectangle. You know rectangle, right? Rectangle in two-dimensional space, that will also be a rectangle. But this is not what I want because this is not axis parallel, right? So in general, an axis parallel rectangle essentially says, in three-dimensional space, right, you can have something like x1, x2 times y1, y2. Those are two ranges, and finally z1, z2. Okay, so the rectangle can be represented as a Cartesian product of three intervals. Okay, this is called a box. Okay, so now I'm going to uh, confine my attention to things that happen inside the box. Okay, so this is what's going to happen next. You understand what I'm saying? So let me say this again. I look at an arbitrary box. I look at an arbitrary box. The box could be the whole join space. The join space is n to the power of 3, right? It could be that, but it doesn't have to. Or it could be just a single point, okay? Anyhow, I'm saying, I will limit my attention to um, the parts of the relations that are relevant only to this box. Okay, see if you can imagine what's coming your way. Okay. Now specifically, you give me a box, and then I can define a subset of this RAB that matters. You see what I'm saying? Okay. So this, oh, by the way, there are two B's here, AB. So that B stands for attribute. Okay, and this the other B. Okay, let me write it into the beautiful B. Okay, so this is a beautiful B, right? this beautiful B represented block. Okay. So what do I mean by this, right? This box B. Well, you see, this box B has has three projections, right? But here you're talking about just A and B. So I look at just the projections of this box on A and on B. You see what I'm saying? So I have two intervals, correct? Okay, good. And then I ask the question, okay, I am interested in only those tuples that fall into the AB projection of the box. Okay, so let's look at this in more detail, right? So let's say small a, small b. You see what I'm saying? Okay. So you can ask the question: does this point AB? This is a two-dimensional point, by the way. I don't have the C coordinate here, right? So does this AB fall into the projection of this box over the two dimensions AB? That makes sense, right? That makes sense, right? Do you have any questions about this? Mathematically, right? So this box has three intervals, projections, right? So I take the projection on A, projection on B, so that gives me two intervals. And then basically that defines so-called orthogonal range query over this RAB. So I mean, so essentially saying, okay, in that subspace containing just A and B, I give you a two-dimensional box, right? And then I want you to find me all the tuples in the relation that fall into the two-dimensional box. Is that right? Okay. By the way, this is something that you can do easily. Okay, so you can. This is a data structure problem that has been very well studied. Okay, so you can have n log n space, and you can find all the such points in log n plus output time. Okay, output is the number of tuples falling inside the box. Anyway, so what I'm saying is, if I give you this box, if necessary, you can retrieve the relevant part of the relation in time essentially linear to the size of this subset. Is that all right? Okay, so far so good. Okay, very, very nice. Okay. Well, if so, and then you should have no trouble understanding, the boxed versions of every single relation. You see what I mean? All right. So I have every right to say, I give you this beautiful box. You find me the relevant subset from every original relation. Okay. Now remember, this box contains the box is in the three-dimensional space, right? So every time you project the box into some subspace, and this subspace corresponds to the schema of that relation. Okay. All right. By the way, as you can see so far, all the discussions can be extended to arbitrary joints, right? Even though I'm illustrating the concepts using this running example here. Very nice. Still remember the definition of a joint. So this is where the definition comes handy. We define a joint as simply as a set of relations. You see what I'm saying? Okay. And now that I have got three relations here, right? Very naturally, I have a joint that is confined to that box. You see what I'm saying? All right. So now I have this QB defined as, just the set of boxed relations that you have. All right. So this is the boxed joint. Okay. So this is joint corresponding to box B. See what I'm saying? All right. So far, so good. All right. So this is a very important concept. Okay. Very important concept. Good. Now, you know that every joint has an AGM bound, right? Time to connect the dots, right? I give you a joint. I'm going to need another 15 minutes today. I'm leaving NTU, so I try to talk about as much stuff as possible, right? So I still have I don't have much time left. Okay, but still, the content. If you want the full understanding, you have to look at the PhD, the notes of the PhD course that I. But still, I try to give you as much as possible. Anyway, so I was saying you have already got this boxed joint, right? And every joint has an AGM bound. Now think about what I just said to convince yourself that this makes sense, right? Why? Because the schema is there. Actually, the schema doesn't change, right? Only the tuples, the content of every relation becomes smaller and smaller, right? It shrinks, right? But in terms of schema, you're still looking at the same schema, correct? All right. And then you know that as long as the schema is there, the schema graph is there, right? And then the cardinality vector, of course, you still have the vector here because I give you this QB, right? The cardinalities are smaller than the cardinalities in the original join, of course, but you still have a cardinality vector. You see what I'm saying? And once you have the cardinality vector, you have the AGM bound for this join, right? So I have every right to say, okay, look at the AGM bound of this QB, right? In fact, more generally, I have every right to say, look at the AGM value of any fractional edge cover W for this join. Now think about whether that makes sense, right? So I give you a W, and this W is the fractional edge cover of the original schema graph, right? So this is a edge cover, fractional edge cover of G. I emphasize this G is not affected by the box. You have to remember that, right? See what I'm saying? This QB still has the same schema graph as before, right? Okay, good. So if I say W is a fractional edge cover of G, right? And then W has an AGM value, okay? Which I denote as this AGM value over the John QB, okay? This is AGM value of W over QB, right? So before I continue, I want you to fully understand this, right? Okay, all right. In fact, if you want, I can even give you precisely the formula, right? So this is RABB. So this is the cardinality. You want to raise it to the power given by this W. So I mean WAB, right? But this is just one term. You still have two more terms here. You see what I'm saying? All right. So I emphasize again that if I give you a box, every relation becomes smaller. However, the schema of the relation doesn't change at all. You're still looking at the same schema. You see what I mean? So if you come up with an AGM, you come up with a fractional edge cover vector on the original John, the same vector can be used everywhere because it's still a fractional edge cover. You see what I'm saying? Okay. Very nice. So now here, this is the crucial concept I need. So this should allow you to have a bigger picture, the following bigger picture, right? I emphasize we have geometry here. You think about you impose some range conditions, right? So one interval condition on every attribute, right? And you get a box. Now this box defines a join. You see what I'm saying? And this join, of course, the result is a subset of the join result of the original join, correct? And now you can define everything over this boxed join, right? You can define the AGM value, you can define the AGM bound, right? So this is what's happening, okay? Now here comes the split theorem. So the split theorem says, so you look at an arbitrary box, okay? And then you want to break the box into B1 and B2, okay? And they are disjoint, okay? And furthermore, their union is the original box. That makes sense, right? So now remember, every box will have to be axis parallel, all right? So basically saying you have to do a vertical cut, okay? Or a cut according to some dimension. You see what I'm saying? Because I have only two boxes here, right? So a two-dimensional example would be something like this, okay? Right? Okay, good. Anyway, so here, I don't confine you how you obtain those two boxes, okay? As long as it's one cut, basically. Okay, good. And then the following holds, okay? So you look at any W. Now remember, W is a fractional edge cover of the schema graph, which is the same for all the box joins. Okay, good. The following holds, okay? The following holds. The AGM value of B1, by the way, does this make sense to you? Now remember, B1 is just a join. Okay, B1 defines a joint, QB1, right? And W is the fractional edge cover of the schema of that joint, right? So you can define AGM value. And what is the formula? If you want the formula, is right here. Okay, good. Plus the AGM value of B2 is less than or equal to the AGM value of the original box. This is the split theorem. Okay. All right, so this is quite easy to remember. Okay, basically it says splitting does not really increase the AGM value. It could probably decrease it. Okay, I didn't say this is equal. You know, the left-hand side could be far less than the right-hand side. Okay, however, you know, this direction always holds, the inequality of this direction. You see what I mean? So this is the mathematical structure I want to review. Okay, so this is known as the split theorem. Okay, good. Very nice. So I promise I will finish, I will overrun for no more than 50 minutes. So this means I still have 7 minutes, which I believe is enough to give you the joint algorithm, worst case optimal joint algorithm. As long as you understand the split theorem, immediately you should see an algorithm. So what is that algorithm? Well, let's apply the split theorem iteratively. You see what I'm saying? In the beginning, you look at one box. You know, that's the box everybody cares about. What is that box? The original joint space. You see what I'm saying? Okay, good. So you look at that box, you know, you split it. You split it. Okay. So here is ABC. You see what I'm saying? All right. So you will obtain two boxes, you know. I hope you like my drawing. Okay. All right. But you understand what I'm saying. Okay. So you got B1 and B2 here. You see what I'm saying? Okay. You can do that. You can do an even split on A. Now, why do I want to do even split? I will keep doing even split because, you know, this is going to confine how many times I can split. You see what I'm saying? Every time I split, before I had n to the power of 3 locations in the box, right? So after that, I have half of that. If I perform another even split, I have half of that or half of that. You see what I'm saying? Okay, and then after a logarithmic number, of splits, what do I get? I come down to just a single point inside the box. You see what I'm saying? So this is going to confine how many times you can split. Okay, but anyway, let's go back to the first split. All right, so starting from the original box, you cut it into B1, B2. You see what I'm saying? Good. Now, importantly, you can test whether the AGM, you can calculate the AGM value of each box in constant time. Okay, once again, I'm ignoring polylog here. Why? Because in order to, so you take W star. By the way, W star is an optimal fractional edge cover of the original schema graph, right? Or when I say original, I really should have said the schema graph of the original joint. Okay, because you know the fractional edge cover doesn't really change, right? Anyway, so let's say you start with this W star, right? Importantly, I give you a box, let's say B1. You are able to calculate the AGM value of W star over B1. Why? Because W star, you already have all the components. They are there, right? And furthermore, you can retrieve the size of every relation confined by the box. So I mean, you can retrieve the size of every boxed relation. Okay, why? Because this is nothing but two-dimensional range counting. You see what I mean? So you take the box B1 and you look at the range, you can look at the projection of B1 over AB, right? So you get a two-dimensional rectangle. So basically you're saying, okay, how many tuples in RAB fall into this rectangle, right? So that's called range counting. You can easily do it in constant time, okay, with the linear space, up to polylog factors, which I don't care. So you do that. And then you can imagine, in constant time, you get the AGM value of B1, you get the AGM value of B2. Now, here is something important. If the AGM value of B1 is 0, and then you are very happy. Why? Because the AGM value, don't forget, it's guaranteed to be an upper bound of the output size, okay? So if it's 0, why do you still have to split it? You see what I'm saying? The AGM value already tells you that the joint result is going to be empty for sure. That's why you stop this branch right here. So let's just say if it's not 0, what do? Simple. You split it again. You split it again. All right. Splitting is basically constant time. Why? Because you have the box, you split it, that costs you nothing. You don't even have to look at the data. But you still have to check the AGM value, which you need, for which you need to look at the data. But I already told you, this is just orthogonal range counting. So everything's constant time per split. Okay. So if you think about it, this defines a split tree. Okay, this defines a split tree. You see what I'm saying? It's a binary tree. Okay, it's a binary tree. However, it's not a complete binary tree. Why? Because you could have certain branch, trimmed away. You see what I'm saying? Okay, because if this AGM value has gone down to 0, you just split it right there. Now let's appreciate the split theorem. The split theorem says no matter what, right? So you look at the leaf, right? You look at the leaf. So this guy's AGM value and this let's say V1 and V2, right? V1 and V2, the AGM values of those two guys is bounded by the AGM value of the parent. And then if you think about it, this is essentially says that you look at any node in the tree, okay, and you look at all the leaves, inside the subtree of this node. You see what I mean? So what can you say? You can say that the AGM value of that node is bounded by the sum of the AGM values of the leaves in that subtree. You see what I'm saying? Okay, good. All right. So that's the algorithm. That is the algorithm. Okay. So to give you a heads up, this is also how we're going to prove the AGM bound in the next seminar. Okay, because now with this observation, you can see that the proof of the AGM bound has made significantly easier. I can tell you the original proof is not something I can explain within an hour. Okay, however, this proof, this AGM split theorem, is definitely something I can do within an hour. Okay, all right. So to sum up, right? So to recap, what is the time? What is the algorithm? The algorithm essentially says you simply do the split repeatedly. Okay, and for every box, you test whether the AGM value is 0. Okay, if it's 0, you stop right there because there's no result there. Okay, otherwise you keep splitting it. Okay, and the height of the split tree you get cannot be very tall. There can be at most log n, actually 3 times log n in this case, levels, right? And when you get to a leaf, right, if its AGM bound is greater than 0, and then it must be 1, because every leaf, every box relation at that leaf contains just one single tuple, right? And then you can test in constant time whether you indeed have a tuple there. AGM bound being 1 does not necessarily mean you have a tuple in the joint result. Okay, you still have to test it, right? But the thing is, how many leaves can you have? How many leaves with non-zero? How many leaves with AGM value 1 can you have? You have at most AGM leaves, right? So even if you test every such leaf, the time is affordable. Okay, good. All right. So this is basically as much as everything I want to talk about today. Just one final remark. So today I didn't talk about how you get a sampling algorithm. Okay, but if you have been following my seminar series, this actually goes back to the sampling to one seminar on tree sampling. Okay, so one very important feature of tree sampling is that you do not really need to materialize the whole tree in order to apply tree sampling. Okay, so for tree sampling, all that matters is that at every parent you are able to calculate the AGM bound of the parent and also the AGM bounds of the children, and then you can make a random decision at that parent accordingly. Okay, so that will allow you to descend one path from root to leaf path. Okay, so using this idea, you are able to obtain a joint sampling algorithm whose running time is AGM divided by out. Okay, so this is another side product of this so-called split tree, right? This binary tree obtained with the split theorem. All right. Okay. So today I'm gonna